Hey, welcome to Transconductance Amplifiers Part 3. This one is on vacuum tubes. So here's a picture of vacuum tubes. We have all different sizes. We have some of the very earliest ones over here. These actually solder into a circuit board, and the rest of them are socket based. We can see they're all different sizes and different types of sockets. We'll see there's actually some more sockets in this too. So the thing about vacuum tube is the voltages. They require a high voltage at the anode to operate, typically about 200 to 250 volts for small signal amplifiers like used in preamps, 500 volts for power amplifiers, typically 400 to 500 volts. Something interesting is there's no negative voltage vacuum tubes. They're dangerous to work, so capacitors will hold a charge for days after the equipment is turned off. So you turn off a piece of equipment, you go to work on it a week later, and it still could have 300 or 400 volts on it. Usually what you do is you short the power supply capacitors with a screwdriver before servicing. Power should be off. When I've done that, I've actually welded a screwdriver to a capacitor. There's that much energy in there. A vacuum tube is called a valve or just a tube. The first vacuum tube was a diode developed in 1904. It has two electrodes, the cathode and anode, and they're placed in a glass tube in a vacuum. It requires a heater or filament. So what we have is a heater here, and the heater, what it does is it heats up the cathode, which allows electrons to flow up to the anode. Here's what it looks like in a diagram. You have your glass tube, a vacuum in there. In the middle up runs your heater. When the tube is on, you'll actually see a little orange light on here. It's heating up, and then we have our cathode is wrapped around it, and around it goes the anode. This is an example of a full wave diode. It actually has two anodes and a common cathode. So we see here's our symbol. We have anode 1, anode 2, we have our cathode and our heater. And this would be one diode and another diode, and they have a common cathode on here. So one of the first things we look at here, this one is super high power. It's got 455 volts going to the anode here, another 455 volts going to here. We have an output here. This is actually our ground. They usually put it through a very low ohm resistor here. And what we find is our cathode is actually our high voltage, and it'll come out at 450. So we get full wave rectification in here. We also have a heater voltage that comes here. Right? So we have a separate winding for our heater. Tube sockets, these are the different types of tube sockets. Tube amplifiers are usually built on a chassis, or you can get them in printed circuit boards now for smaller ones. And this is an example of a chassis mount one here. Is you drill a hole in a chassis, and then you drill a couple holes, mount this in. This one looks like it's for a printed circuit board. When we look at a diagram, what we'll have is our diagram of our cathode heater, and then we'll have our pinouts here. A lot of times what will indicate is what the actual pins are on our diagram as opposed to their function. This is looking from the bottom view, right? So bottom view, you would go clockwise, starting from there's a little key here. So over here, here's our key. That's pin 1, 2, 3, 4, 5, 6, 7, 8. And normally you're looking at it from the bottom. So the bottom, you'd have to reverse it. So one of the things working with tube amplifiers is you get used to your perspective, which side of the chassis are you looking at. On the heater voltage, the power transformer will have a separate secondary winding called a tap for the heater voltage. So we got a tap over here, or a secondary winding. This one's 6 volts AC. The typical heater voltages are 5 volts for rectifier tubes, 6 or 12 volts AC for most others. And the very first rule is there are no rules. There's all sorts of different voltages for heaters. The first digit in the tube name is the heater voltage. So this one is a 6CA4. So the 6 means that it's a 6 volt AC heater over here. So we have a transformer that's 275, 0, 275. So we got 275 center tapped with ground. So we have another 275 here. 275 here. Across from here to here, there's 550 volts AC. So we deal with lots of voltage. Then it comes out here and it's rectified. European numbering, a North American 6CA4 tube is a 6-volt AC heater, 6 volts here. And the European tube is a EZ81, same tube, just different numbering. Europe usually uses EZ or EL tubes with a number like this. Sometimes they use just plain numbers like 6581 or something like that. This is a miniature tube socket. It's a 9-pin top socket, and this would be the pinout that you'd get from a spec sheet. So it would say, looking at this way, pin 1 is the anode, A. Pin 2 is not connected. Pin 3 is cathode with a K. Interesting, back in the day, we used to write cathode with a C, but mark it as a K. F and F are filaments, another name for saying the heater, not connected. Anode prime, which means it's a second anode, and that not connected, not connected. And there's no keyway on this. What they have is a space in here, so the tube will only fit in. There's a little gap here. This is an example power supply. So what happens is that you have your 6CA4 full wave rectifier. We got our 288 volts here. It goes to a capacitor. And then what they do to get other voltages is they'll put a resistor in series. And the resistor is typically like 5 watts. It's a huge resistor. It will get hot and burn you. And then they actually use inductors. Inductors are current storing devices, so they'll keep a constant current, and they also block AC. So we have capacitors will charge, get rid of any AC ripple, and then we also have an inductor which will block AC past DC. Also a little bit of resistance in here, 56 ohms, and it drops the voltage down to 255. So one of the things is the voltage will change with the load depending on what it's doing. So we'll find that this is an approximation. We'll expect that somewhere between here there's a roughly 30 volt drop. And over here we'll put another inductor, and this will be another tap. This will go to a different section. This might go to a preamp. And what we'll find here, this one might go to the power amp, this might go to a preamp, and it might go to another preamp section. And we'll put another inductor in between to clean up the power supply a little bit. And now we'll get 247 volts or so. It could be 250, could be whatever, a little bit of voltage drop here. And that's called B+. So in tubes, the power supply is called B+, transistors, it's VCC. One of the things they do on tube amplifiers is that they use the chassis as ground. So this is an example of a chassis. It's kind of neat is you put your tube sockets in here. You got a little bit tinier ones. These are the preamps. These are probably power tubes. And what you'll do is you'll have grounds, and you use the whole chassis as a ground. So we'll use terminal strips like this one, and the center one will be our ground lead, so we can ground it, grounds the chassis, pick up ground over here from another point on mechanical point. In the old days, when I worked on these, what happened is that you'd use a soldering gun, or if you couldn't afford a soldering gun, you'd use one of these old big soldering irons, and you'd actually heat up the chassis and solder directly to the chassis. Nowadays, what happens, you can get tube sockets that sit on circuit boards, and it makes it a lot easier, but this is a lot more fun. So the first tube we're going to look at that's used for an amplifier is called a triode. Triode is because it has 3 leads, the anode, the grid, and the cathode. We don't consider the heater as part of it. It's just to heat up the cathode. A grid is added between the anode and the cathode. So what we have is we have our heater. Wrapped around our heater, we have our cathode. And then on the outside, we have our anode. In between, we put a grid, and it's actually a grid of wire. And that's this part here. Now, what happens is a small grid voltage. Let's say if we put a positive voltage on here, what we're trying to do is we have our cathode is going to emit electrons to our anode. If we put a positive voltage on here, the electrons are going to be attracted more. We'll get a higher anode cathode current. If we put a negative voltage on here, what happens is the electrons are going to be repelled a little bit, and we'll get less current flowing. So what happens is that's the definition of transconductance. A little bit of voltage is controlling a lot of current. Tubes use conventional current flow because basically it wasn't until semiconductors that came out in the 50s that they really started to understand about electrons and electron flow. So normally it was thought that current flowed from the anode to the cathode. Here's an amplifier example. This is a guitar amp. So basically we have two inputs here. We have an input, it goes into the grid, and then we have a cathode resistor, which is very similar to an emitter or a source resistor. And then we have our anode, very similar to a collector or a drain. And this is an inverting amplifier, so we take some voltage in and then we get an inverted signal out. This is at very high voltage, so typically for a preamp, this uses a 12AT7, so it says valve 1 is a 12AT7, so this is valve 1A and valve 1B. So this is a dual tube, dual triode tube, very common one. A lot of times what they'll do is they'll draw dashed lines here to indicate that it's half a tube. So what happens is this comes out here because we have high voltage and we don't want high voltage on the grid. The grid is usually at ground or very low potential. We'll put a decoupling cap. That'll let the AC signal to block the DC. So here we'll just have our AC signal. We have a bass control, a low pass filter lets the bass through. Then we have a high pass filter that lets the highs through. We come up to our second stage. Again, we have a cathode resistor. That one is used to establish our DC biasing. And that we have our inverted again output. We have a coupling cap that takes it to a volume control. This would be our master volume control, which then goes to a third stage. One of the things they indicated that this is shielded wires. So as it goes through the chassis, as it travels, you want to put a shielded wire on here so it doesn't pick up noise. Over here we have this capacitor here. This is a capacitor that what we can do is this resistor is used as part of the AC gain, but if we short it to ground, then we don't need this resistor here and we can manipulate the gain separately from the DC component. Third tube we're going to look at is called a pentode tube. This is used for the power stage of an amplifier. The penta is the number 5, so it adds 2 more grids. So we have our plate or anode. Plate is another name for anode. Usually when we talk about power tubes, we talk about it as being the plate. And we have our cathode, we have our grid, and then we add 2 more grids in there. We call it the screen and the suppressor. The screen is a slightly lower voltage than the plate to reduce the Miller capacitance effect. So what they found is that without a screen, there would be a capacitance in here and we'd then build up a charge and we'd end up with problems. I always like to think of the screen as that it aids in those electrons to be attracted to the plate. Right? The suppressor, what would happen is electrons get really excited from the cathode and they hit the plate and then they bounce off the plate, and they have sufficient energy that we start getting electrons being bounced around. So what the suppressor does is it captures these electrons to prevent instability. One of the instability, you could get a runaway tube would start heating up and heating up. As it started getting more current, more electrons would bounce off. As they bounced off, they would start cycling. Next thing, you'd have a runaway tube and it would just overheat. The extra grids allow higher voltage and power to be utilized. So that's why we use these pentodes too. Is now we can actually start pushing some power out of these things. And power in this case is current. We want current to go through. So if we take a look at a power amplifier, this is a push-pull power amplifier. We have our B plus coming into the center tap of a transformer. One side of the transformer has one pentode, the other side has another pentode. We have a special tube here called V2B, is called a phase inverter. So it takes an AC signal in. It comes in actually from the previous stage that we saw when we talked about the master volume control and the bass treble control. And off the anode, it's inverted, so we get an inverted signal. So the top tube is going to do an inversion, and the bottom tube is a voltage follower, call it a cathode follower, and we have the same phase. So it comes into these tubes. So while this tube, we'll start here, while this tube is going positive here, this tube is going negative. So we're getting a nice current flow through here. So this one is going positive this way, and this one is going negative this way. So we're combining this out to our speaker. So we call it push-pull. So while this guy's pushing, this one's pulling. When he starts pushing, this guy starts pulling. This is what a power tube amplifier looks like. This one's a time-lapse picture, so you can actually see all the colors of the filaments and the heaters glowing. It actually doesn't look this dramatic. This is just a pretty cool picture. And that vacuum fluorescent displays, they actually use a technology that's very similar to vacuum tubes. Each segment has a mesh grid, anode and cathode. So it's very similar to a triode. So each one of these little segments that are lighting up, there'll be a lot of dots here, is similar to a triode. Nutubes is a triode based on vacuum fluorescent technology. This came out in the last 5 years, and what they did is they built basically a vacuum fluorescent tube here, and this one's has 2 of them, and now they're basically triodes, and now we can actually create circuits that are quite a bit smaller and take quite a bit less energy. Typically they'll run at I think the filament, they have a filament on there, and it'll run like 2 volts or something, 5 volts, and it'll run less than 20 volts. So now we have the characteristics of a vacuum tube on almost a semiconductor-like material. So advantages to vacuum tubes: they're not susceptible to radiation and energy bursts from a nuclear explosion. So for a long time, the Russians, their jet fighters were all vacuum tube based, because in case if they were close to a nuclear blast, their semiconductor systems, their control systems will survive, where if you have a semiconductor system, it will not survive unless you have lots of shielding and that. Transistors clip, which cause odd harmonics, which is unpleasant to the ear. So over here we have in blue, here's a sine wave input, and what happens is it's basically overpowering the transistor. So what a transistor will do is it will clip the signal. These are odd harmonics, and they're kind of harsh to the ear. They're unpleasant. And that if you ever heard some guitar distortion that's really unpleasant, that's what you're hearing is odd harmonics. Tubes distort with even harmonics, which is pleasing to the ear. Now what's interesting, as a tube gets to what we call clipping, instead of clipping, it starts rounding the signal. So instead of being a sine wave, it starts rounding it. And what it's actually doing is adding even harmonics. Even harmonics are pleasant to the ear. So we can think of you have a C, and then you have 1 octave up. That would be the first harmonic. So it actually makes it sound better. And what you'll see is a lot of guitarists like tube amps, because when it distorts, it adds a more pleasing even harmonic to it. So what we find is guitar and audiophile really like tube amplifiers. So over here we have a tube amplifier in a guitar amp, and typically they hang them upside down, and that's just so the controls are easy to get at, and then they can stick these down here. Something else about tubes is they can be harmonic, and that is an issue with, if we go back to Nutubes, one of the problems with Nutubes is that they are harmonic, which means that, or microphonic is a better word. Microphonic means that they will pick up noise and vibration. So one of the things when you design a board with a Nutube is you have to be aware that it could be microphonic, and you might have to put some physical isolation around it. So power tubes are not normally microphonic, but preamp tubes are. Sometimes what you'll do is you can see what looks like a cylinder back here. Is what they'll do is they'll actually shield the tubes. They will put a metal shield around it and ground it, so you can have shielding that way also. Here's an example of a stereo audiophile amplifier. Part of the reasons that they'll use something like this is that when you listen to stereos, you might only listen at maybe 5 watts power. But what you'll find is the peaks might hit 20 watts or 50 watts or 100 watts for instantaneous when something happens, like a cymbal crashes. Well, that's the time that you need the overhead, and you don't want it to be clipped. It could be acceptable to have it rounded off and give a pleasant distortion. That completes Transconductance amplifiers, and I hope you enjoyed it. Thank you.